Give an exam and a homework due Tuesday. 29. We'll have the same study. You guys have taken sufficient courses with me. Same style, everything. So probably 4 or 5 questions, relatively small, which is coming out of your homework problems. Okay. We constructed the Green's function for our problem. So let's go back and look at what we're doing. We introduced time dependence in the problem. Or not introduced, we did not bother to go into static limit. So in the Maxwell's equations now, we have, so let's say magnetic field is given in terms of del cross A, and the electric field is given in terms of negative gradient of scalar potential and the time derivative of the vector potential. So in terms of the vector potential and scalar potential, or the electric potential and the magnetic potential, the electric and magnetic field is given. These are all time-dependent quantities, position and time-dependent quantities. And we found that we can write the equation for both the scalar potential and vector potential satisfy the following conditions. So this R, comma T. And the same equation holds for the vector potential also. Both are given by the wave equation. If this was 0 on the right hand side, that means there was no electric charge around, or if there was no currents there, then it is indeed a wave equation. Otherwise, there is a source for the wave equation. So it emits quantities, and here it is the charge density. Charge density. And if it is for the magnetic potential, it is the current density. And of course, if you set t equal to 0 here and say that there is no time dependence, that goes back to your scalar potential, also electrostatics and magnetostatics. Once we have the scalar and magnetic potential, you get the electric and magnetic field, and you can work around. The main difference now is the time dependence. For this purpose, we said if we want to work in this scenarios, it's good to construct a Green's function. So we went ahead and constructed Green's function, which is G R minus R prime and T minus T prime. So we are saying that there is a single point charge at position R prime at time T prime. And what will its contribution to the potential be? And this says that it is at position R prime and at time T prime. And we found the solution for this. the solution for this Green's function was pretty much very similar. It's expected that it should contain the static version of it. So that's 1 over 4 pi r. So this is 4 pi r minus r prime. That's a point charge. But now the time dependence in this is given by a delta function of t minus t minus t prime c. And it's a nice interpretation that if we have something happening at t prime, the observation at t is delayed by the amount of time light takes to travel the distance between the two, between the observer and the time. We will find it convenient to should we define it now? T minus. Yeah, let's leave it. Yeah, so let's yeah, probably. So we will define a retarded time. Retarded time will be defined as TR is equal to T minus 1 over C times R prime. Like time should have been this, but it is retarded by a certain amount. So that's the retarded time. Okay, so that's our building block. We would like to solve these two equations. We know that these two can be solved in terms of the Green's function. This is like saying if we know a point charge, we know the electric potential, add up all the point charges, you get the complete electric potential. Now we don't not only have to add up all the point charges, we have to add up all the times also. Add all the time contributions, add all the position contributions, and that's the superposition principle. Right? So our solution would be phi at r comma t prime or t, sorry, that's the observation point, would be equal to 1 over 4 pi epsilon naught, right? That's coming from this 4 pi here and epsilon naught there, and d cube r prime, that is add up all the contribution from all the sources, right? There is one source here. If you have many sources, add up all the sources. That's what this, and then add up all the times also. We have to add up all the times, all the way from minus infinity to plus infinity, and put in your Green's function. So that's t minus t prime minus 1 over c r minus r prime divided by r prime, and we have a row of r prime and t prime. That's your sources. Add up all the sources wherever this contributes. This integral contributes, and that's a contribution from each position and each time. Is that clear? And the same thing you do for vector potential. So if you mu naught over 4 pi this time, q prime P prime. So this is over all space. So basically, you're scanning for all the point charges that exist both in space and time. That's your source points, and that's your superposition principle. So whenever we want to have we want to find the electric and magnetic field due to a moving charge or moving charge distribution, find the scalar potential, vector potential. So these two are given to us. Using these two, get your scalar and vector potential, complete these integrals, and then use your electric and magnetic field is just simply got by taking the derivatives. And even though it is stated very well, like this is easily stated, we will notice that this is typically a little lengthy process, tedious, and often not easily doable. But let's do a solvable problem to begin with. So let's consider the following scenario. So a moving charge, if a single charge moving with a uniform velocity. That's pretty much the simplest motion you can think of. If you have a point charge at rest, we know what's its electric and magnetic field going to be. Now we are saying that there is a simple point charge that is moving with uniform velocity. Okay, how do we describe it? So we would like to know, if we want to do this, the first part is to get my charge density and the current density, put it in this, solve for this, and right? That's our procedure. So let's describe this to begin with. So there's a simple positive charge, let's say Q. Positive charge Q, it's moving with uniform velocity V. Let's say it's moving in the Z direction. Here. That's a straight line motion. And let's say this is in the Z direction. So that's your Z direction. That's Z hat is in the same direction as your charge is moving. Let's say at t equal to 0, its position is 0. So its position is Z. Position is R, right? So let's say, so position vector is R. R as a function of time will be X as a function of time in the I hat direction, plus Y as a function of time in the J hat direction, plus Z as a function of time in the K hat direction. Let's say it's on the Z axis, right? That's it. Yeah, for simplicity. So let's say this is on the Z axis, so it's 0I. It's on the Y. Did I say X axis? No, it's on the Z axis, I said. So it's X is 0 and Y is 0. So it's 0J. And Z position, it changes with time and it evolves as velocity V times T. So let's say this is V times T, the K hat direction. This has this added feature that at t equal to 0, it is simply 0. Right? At t equal to 0, position is completely, it is at the origin. So we are talking about a point charge that's moving on the z-axis with uniform velocity in such a way that at t equal to 0, it's at the origin. That's your position. Now we want to write what is our charge density and current density. So let's go ahead and say charge density. So charge density is R times, let's say R prime and E prime. since we want it in R prime and T prime, so we just have to replace all this. But how does this work? This is a point charge. So it is charge Q times point charge is described by a delta function. So this is delta function, delta of x, x prime minus, where is it? It's at x prime equal to 0 all the time. Right? X prime is the coordinate, and where is it at x prime? That's decided by 0. And times y, which is y prime minus 0. So its position along the y-axis states that it's 0, and z prime is vt. And since it is t prime, we are working with it is t prime. Is that clear? That's how you would write your charge density. If it was at the origin static, then you would set this to 0, and indeed x prime, y prime, z prime is 0. It's at the origin. But now that it's moving, every time at each time its position changes and the delta function position changes accordingly. Any questions here?
That x prime means what is the position at x prime? I mean, 0, that's why you put it 0.
Exactly. So it will select the position, right? When you set the argument of the delta function to be 0, it gives you where the position is. So since it is at 0, x prime is 0. So that's why I set it. In general, you have rho to be delta cube of r minus r cube, where this is the position of the charge at time t. Let's say this is at time t. In general, that's how you would. Okay. What about the current density at r prime and t prime? That's equal to you multiply it with the velocity, and that's all. So it is q times. It is basically how should I say it? Yeah, it is v times charge density. That's your, for a point charge, that's your current density. But v is, what is v? So I had to take the derivative, right? So velocity as a function of time is equal to 0i plus 0j plus, when I take the time derivative, it's simply v times k. It's clear? It is moving in the z direction. So this is equal to k hat. So k hat times v times q, or q times v, times again the same delta of x prime, delta of y prime, delta of z prime minus vt prime. This time I did not write the zeros. Okay. So that's the input if you want. That's how. That's the configuration for our charge, movement of our charge, described in terms of charges. There's a single point charge, the simplest problem you can think of. If we put this in here, do the integrals, we get the potential, and that's what we want to try to do. And notice that everything is retarded, right? So the delta function picks up all the retarded times. Okay. Any questions at this stage? Okay. So we try to put this in. So let's start with one thing we can immediately see that if I were to replace this j in here, right? So the only difference between j and rho is this v times k. if not for this piece, this is exactly, so maybe I can write this as V times K times rho hat. And if that's the case, I can, if I put V times K hat times rho hat, it's the same as phi. And the whole V of K can come out of the integral because these integrals do not care for this constant V and K hat. So I can pull this all the way out. So notice that A of RT is equal to, I will put a mu naught times C naught, right? Sorry, I didn't mean C naught, epsilon naught, because I want to divide that, times V times K times the phi for a point charge. In fact, it will always be V times that. So this is equal to V over C square times K hat times, let's say V over C times phi or T over C. Is that clear? So if I get my scalar potential, my vector potential is obvious. Right? This just multiplying the velocity gives me.
Now, how do you get me zero in zero?
Oh, because there is this epsilon naught here, right? So I multiply by an epsilon naught, divide by an epsilon naught. And whatever is with the epsilon naught is my phi. Is that clear? So that's fine. Because phi has this epsilon naught, but it is not there here. So I provide that by multiplying divide. Okay. So it's clear that we should concentrate our time on getting our scalar potential, and the vector potential is straightforward from that. Okay, so what is our scalar potential then? So scalar potential phi or comma T is equal to. So let's explicitly write this. So that's 1 over 4 pi epsilon naught. That three integrals, I want to write that more explicitly. So this is x prime, y prime, and c prime. And we also have a t prime, dt. And the delta function is delta of t minus t prime. It's 1 over c. R minus r prime magnitude, remember, is x minus, so this is nothing but x minus x prime square plus y minus y prime square plus z minus z prime square. Right? That's a definition of r minus r prime square. And divided by the same here, square, x minus x prime square plus y minus y prime square plus z minus z prime square. And we have to put in our charge density, so that's Q. I take my Q all the way out. And that is a delta of x prime, delta of y prime, and delta of z prime minus v t prime. Clear? Okay, so we know how to do these integrals. Let's do x prime. Whenever there is a delta function, the integrals are straightforward. set x prime equal to 0, set y prime equal to 0, and z prime equal to vt prime. So 3 integrals are immediate. So let's do that. So that's q over 4 pi. Oh, there's a 4 pi epsilon now, right? Missed pi epsilon naught. Right. 4 pi epsilon naught. It's q over 4 pi epsilon naught. The 3 x, y, z integrals are done. So this is only time integral remaining then. dt prime. So this delta function I'll keep. Or I can do that also, but you'll see that that's a little tricky. The denominator x prime becomes 0. So that's x squared plus y squared plus z minus, instead of z prime, it is bt prime now. And here the same thing, 1 over c x squared plus y squared plus z minus bt prime squared. That's and that should also be straightforward in the sense that delta function is typically easy to work out. So wherever this goes to 0, that's where this will contribute. And it will contribute exactly at like the contribution coming from the charge in a retarded time. You have to go fast, right? If I get my postal mail today, that means if I go back in time, the post started from Chicago somewhere yesterday or day before yesterday. Right? So the information content will be based on yesterday in this. Okay, so that's the idea. But formally doing it, it's harder because this we have to find now the roots of this delta function. So let's think about so how do we find how do we evaluate delta functions of this kind? Well, let's take a small digression. So let's talk about delta functions. So we know delta functions, but we want to find identities related to delta functions. So let's talk about how do we say this? But if we have a clearly delta function contribution comes whenever the argument of the delta function goes to 0. That's our understanding. And let's say the delta function is having 2 solutions. So let's say there is x squared, let's say 3 and 4, correct? So it is x squared minus 7x. And this x has nothing to do with this, is just a general variable. Okay. So 3 equal 12, let's say, so it's plus 12. So what is that equal to? You first say that, okay, that's a quadratic equation. If I want to know where does this delta function contribute, I have to first find the solutions for this. So what are the solutions? X squared minus 7x plus 12 equal to 0. What are its roots? You say that, what are the roots? 3 and 4, right? So it is 3, 4, that's 2 roots there. So the idea is that you do delta of x minus 3. That's one of the solution. And the second solution is delta of x minus 4. So that's the second solution. Okay. So that's the 2 places it will contribute, and it is a positive. But that's not all. There you also do, there is a factor coming in these 2 situations. So to determine the factor, what you do is take this piece here, whatever is the polynomial or the function inside the argument, take the derivative of that. So derivative of that is 2 times x minus 7. And then evaluate that at x equal to 3. Okay. And then take the magnitude. It's a lot of steps. Take the derivative, evaluate it at x equal to 3, and then take the magnitude. Okay. Do the same thing here. The derivative is the same, 2x minus 7, but this time you evaluate it at x equal to 4, and then take the magnitude. Okay. So that comes out to be equal to, in our situation, so 2 times 3 is 6, 6 minus 7 is minus 1, but I have to take the magnitude, so it is delta of x minus 3 over 1. And the second is delta of x minus 4 over 2 into 4, 8, it's again 1. Right? It's again 1. And in general, you can have an identity for it like that. So in general, what you do is, suppose you have a delta function of, let's say, a function which is f of x. Okay. So if it is a general function, the first thing you do, what we did was find the roots, right? So find the roots of the function. F of x equal to 0. And whenever it is 0, let's call it x of r. Right? That's the roots of the function. It can have more than one root. In this case, this has 2 roots. It could have multiple roots. It could have infinite roots. So however it is. And each root contributes, right? 1 plus 1. So you sum over all the roots. Sum over all the roots. So R is the roots. Sum over all the roots. And in the numerator, you have x minus xr. Right? That's your x minus 3 minus 4. And in the denominator, we took the derivative of f of x. So take the derivative of f with respect to x, evaluate it at x equal to the root, and then take the magnitude. That's a useful identity. And as a quiz, prove this. It's look it up on the internet. It's sufficient things are there. And even if you, I think if you go back into E&M, you didn't take E&M with me when we do electromagnetism. The first part, when I do it in the first week. I do delta function. So if you go into past lectures, you should be able to see it. But just again, remember, quiz, you don't have to go through in detail. I just evaluate on the basis of whether you have attempted or not. So try to prove this, or at least try to have a feel for what that is equal to. Okay. So now we know how to proceed, which means that I have to solve for this equation, correct? I have to find the roots of this equation. So let's do that. Where's this spot? Okay. So to evaluate this integral, I'm going to evaluate the roots of that argument. So let me define f as a function of t prime, because the variable is t prime, not t. That's the integral variable is t prime. That's where I want to set to 0. So this is t minus t prime minus 1 over c, and this is x squared plus y squared plus z minus bt prime squared. When we are looking for the roots, we are saying that this is equal to 0. Let's say the roots of PR, that's equal to 0. Whenever is a root, that's equal to 0. That means we have to set that to 0. So set that to 0, and we want to solve for PR. So let's square that, right? So it's a standard thing you will do. T minus TR squared will be minus 1 over c squared and squared plus y squared and minus z minus vtr. That's equal to 0. Correct. That's here. That's the equation we want to solve for TR. Like we want to find the roots of TR. How many TRs will be there? How many roots will be there for this equation? 2, because its power is 2. It's a quadratic. It will be a quadratic equation, and it will turn out that one will be in the past and one will be in the future. So only one of them will be relevant, but this will give us 2 times when this function goes to 0. So this delta function, in principle, evaluates at 2 points, but one is not causal. One is in the future. Okay, we want to construct this delta quadratic equation. So square this and write it as a quadratic equation. So let's do this. So this is t squared plus tr squared minus 2 times t times tr minus x squared plus y squared over c squared, and this is minus z squared over c squared, and that is a minus v squared over c squared times p of r squared, and there's a cross term, so it's plus 2 times v over c, z over c times g. That's explicitly, bluntly doing it. Let's collect things together. So that's tr squared 1 minus v squared over c squared. So that's the 2 terms contributing to tr. Notice the structure coming up, 1 minus v squared over c squared. And remember, Maxwell's equations are relativistic by construction. Like that's to begin with, they're relativistic. Like that's what led to the relativity of Einstein. So that's what is already showing up. We didn't change anything in our Maxwell's equation, but it is relativistic to begin with, and we'll see the connections soon. We want TR also, so let's collect the TR terms. So let's write it as 2 TR, and that's T minus, this is plus or minus outside, so it is V over C, Z over C. So that's these 2 terms gone, and finally whatever is remaining is plus T squared minus x squared plus y squared over c squared minus z squared. We're going to process this a little bit, but it's clear what the solution will be. So PR would be the retarded time will be equal to minus b, right? So minus b is minus plus, so plus 2 times t minus b over c, c over c, plus or minus. And again, square this. So this is 4 T minus V over C square minus 4 times 1 minus V square over C square, 4 times A times C. Messy, but that's what it is. And that's a numerator, and denominator is 2A, right? So it's 2 times 1 minus V square over C square. The 4's and 2's cancel out, so 4, I can pull that 4 out, and that's what the square root can be processed a little bit and written in a slightly neater way. So let's do that here. So the square root part alone, this part alone. So let me write that as a square root in this square root part. The square root part is T squared plus V squared over C squared times Z squared over C squared minus 2 times T V over C Z over C. Just expanding this out. So, and then we have minus T squared what should I do? Yeah, I think so. I think that's, I can write this as minus 1 minus V squared over C squared times T squared and plus 1 minus V squared over C squared times X squared plus Y squared plus 1 minus V squared over C squared times Z squared. Okay. Notice there are some cancellations. This T squared apparently cancels this 1 here because minus T squared is there. And V squared, C squared, Z squared, C squared, that cancels this term here. And whatever is remaining, let me collect them together. Here I have V squared C squared times T squared. That's this term. And I have minus 2 times T V over C times Z over C. And let me collect this plus V squared C squared. Basically, processing this out. And whatever is remaining is plus 1 minus V squared. It is 1 over gamma squared, right? 1 minus V squared over C squared. This is a total square. That's what I was trying to capture here. So this is nothing but Z minus VT squared. And the other one is simply plus gamma squared if you want, but let's write it as 1 minus. So we have our retarded time given by so that's equal to T, the candle speed processed, this stays as this, so T minus C over C, C over C, and all these factors that we show or see in different combinations, these are all relativistic contributions, like 1 over V over C, and since we are not used to it, that's why it seems like an odd construction. And this is plus or minus and square root of this. Let me write that as x squared plus y squared plus c squared times 1 minus v squared over c squared. And the other term is actually I can pull out the c, right? Pull out the c. 1 over c square root of x squared plus y squared and we have plus z minus vt squared. It's still the position of the chart, right? Except now the lengths are getting contracted. Remember, all the lengths contract, right? And then 1 over 1. And I can write that as 1 minus square over c square times okay. So that's our TR, but now we have to evaluate it. So there is a lot of work remaining, right? So now we have only found the roots. The roots itself look very, it doesn't look pleasant. But now we have to evaluate the roots, 2 roots, and then divide it by the derivative of this argument at the roots. So let's see what that is equal to. So right away, let's evaluate the derivative. But before that, maybe we should argue that one of them is causal. So how can we see that? So at time t equal to 0, right? At time t equal to 0, let's see what the retarded time is. Right? Retarded time, if it is negative, then it is not causal. Right? If it is retarded time where was it? Yeah, retarded time should be t minus some quantity. So if t was 0, then if it is negative, that is okay. Right? If it comes out to be positive, that means it's in the future. Right? T minus something, that's when it should contribute. But if it by any chance is positive, that means it is in the future. So let's set t equal to 0 and see what this is. So T of R at t equal to 0 is, and make the v very small. So yeah, so T of R at t equal to 0. So that's equal to minus v over c, z over c plus or minus 1 over c x squared plus y squared 1 minus v squared over c squared, and this is plus z squared. It is very clear that if it is negative, it is surely in the negative pieces surviving. But if it is positive, we have to see whether it is, can it be positive or not. But notice that the z and v term is already here, right? So z and v term. So in a square root, that is a z over c term coming from here, and there is a v over c term coming from here. And there are other pieces, so that it will be always bigger. So one can argue that this will always be causal. So the positive sign out of plus and minus, this is minus is causal. This is not causal. Okay, argue that out more carefully, and from this point on, then we can drop that. So we will not talk about. So there are two contributions in principle, mathematically speaking, but physically we remove that not causal term. So our solution then for electric potential would be the electric potential would be then Q over 4 pi epsilon naught first. Let me write this as minus infinity to plus infinity. Write this as a single delta function. This gets contribution only from T minus TR, right? Only from the root, and that's equal to, and that is a square root, right? So that's a derivative of f, which is this function here, with respect to t prime, and evaluate this at t equal to tr, and then take the magnitude. And the other piece remains. This is due, so this is t prime, sorry, right? That's t prime, this is also t prime. So t prime has to be replaced with tr. The only place where t prime shows up is here. Rest everything is anyway the delta function part. So this is q over 4 pi epsilon naught. Still requires processing, we will see. This is tr now. X squared plus y squared plus z minus vtr square. And this piece is 1 over derivative of f with respect to t prime, evaluated at t equal to tr. That's our electric potential. So we have done all the integrals, except that we have to process this. Right? It is algebraically tedious at this point to put it in the right form. What is the derivative of the function f with respect to t prime? So let's here maybe. Okay. Any questions? It's clear what's going on? Is the pieces? Yes.
You replace the t prime with tr, the retarded time, in the like 1 over square root situation.
Yes. Tell it again. So this is t prime. Yeah.
Yeah, I was just curious why.
Oh, because we are evaluating using delta function, right?
Hmm.
The idea of delta function integral is that replace t prime with tr in every where function is.
Oh, f of a, right.
Right.
I see.
So yeah, like, that's a delta function property.
I see. Thank
So
you.
when you're integrating, it's straightforward. Just replace t prime with tr.
But there is no t prime. So
Here,
here is no t prime.
no, t prime is replaced with tr. So this is the root. So I have to go back into, or this is at this tr, it will contribute. Ask me again, Okay.
So my question is, you are evaluating df by dt prime, yeah. So the df prime, in the TR there is no t prime.
It shouldn't be, right? So for example, if I were to solve for this quadratic equation plus 3t prime plus 5 is equal to 0, the t prime is tr, right? So whenever t prime, this is the root, right? This will have numbers, right?
Yeah, now I get it.
Correct. So tr should not have any t prime in it. Like that's the special value of time when this goes to 0. Right. So if I were to put this tr, replace it with t prime, that will go to 0. But the derivative will not go to 0. Right? That's what will contribute to it. So the idea is, okay, what is the derivative? So we have to go and calculate the derivative, right? So let's calculate df by dt prime is equal to, that's not that bad. That is minus 1 there. And that is minus 1 over c. Then there is 1 by 2 coming from the square root. And the square root goes to the denominator. So it's x squared plus y squared plus z minus vt prime square. And then take the derivative of the argument. So that's 2 times z minus vt prime and then a minus v. That's your derivative of that. That is a minus v plus v, so that's, this is equal to, let's say, minus of, so minus 1 plus v over c times z minus vt prime over x squared plus y squared plus z minus vt prime squared. I will be interested in the when the evaluation is done at TR. So this is dt prime at t prime equal to t of r. And I have to take the magnitude also, right? But notice z minus vt is always smaller than the denominator, right? Because this is added, right? 2 positive quantities are added to this. So this will always be less than 1. This is always less than 1. So this whole quantity is less than 1. This is a minus 1. So magnitude will be 1 minus of this. So I have to switch the sign of this. So this is 1 minus v over c times z minus vtr over x squared plus y squared plus z minus vtr squared. So I can replace that here. Right, at this point, so let me use that. So phi of r as a function of time is equal to q over 4 pi epsilon naught 1 over x squared plus y squared plus z minus vtr squared square root, and then this is going in the denominator, right? So it is 1 over 1 minus v over c times z minus vtr over that's your electric potential due to a point charge, which is moving, and this is your T of R. Everywhere it is retarded time, so it kind of readjusts its x 1 over distance. But let's rewrite this in a little covariant form. So let's process this so that we can actually see it as a relativistic contribution. Like why each piece is there, right? So put this in, this cancels this. So there's a small tiny simplification in there. So that's equal to Q over 4 pi epsilon naught. So it's 1 over square plus y square plus z minus VTR square minus V over C times Z minus VTR. Okay. Still not in the perfect form we would like to interpret it in, but this is one simple form. But look, what is that equal to? So let's see. This can be written as an easier way of writing this a little bit. Yeah, so let's actually process this here. This can be simplified significantly, which is easier to interpret. Notice that when TR is equal to 0, this is equal to 0. This whole thing is equal to 0 at TR. Is that clear? So let's do that. So when this is equal to 0, this implies that C times T minus TR is equal to 1 over C times x squared plus y squared plus z minus VTR squared. Is that clear? Oh. But I'll go back. Nevertheless, let's when this is equal to 0 means that this is equal to 0 at a substitute T of R, and that's equal, correct? Right. So that means to say that wherever I see this expression, I can replace it with T minus TR. And that's exactly what is showing up here. So use that and I will get use that and we can write this as just an intermediate step. So this is C. C times T minus TR minus V over C times V minus V up. I have to do this carefully. And then one more step, only one more step, I suppose, and that is you write collect the TR separately. One more step, it's equal to Q over 4 pi epsilon naught. Put the C in front. And what I have is 1 over. So I've taken the C out. So this is T minus V over C and Z over C. That's this piece and this piece. And the TR part is equal to plus TR times times TR. What do I want to write this? TR minus minus TR. Minus TR, and then there is 1, right? Because C I have taken out. That's gone. So this is plus now. I need a plus, so I need to write a minus. There is V over C and V over C, V square over C square. But TR times 1 minus V, that's this, right? And this one is this, right? So this minus this would be this whole thing under the left. So I can replace that. So maybe we should write that here before we move the camera a little bit. So 7, 8. So write this as this leads to I have T minus V over C times V over C minus of 1 minus V square over C square times here is equal to, remember minus is a causal solution. We bring it out, so it's 1 over C square root of x squared plus y squared times 1 minus V squared over C squared plus C minus VT squared. So my Green's function is like this one. Yeah. This is equal to then. So after jumping on steps, so this is over 4 pi epsilon naught times there's already a 1 over C. Is an extra 1 over C. 1 over C is that 1 over C squared, maybe? Let's make sure I'm doing this right. Yeah, why did I get this extra C?
Yeah. You took 1 by C, right? Yes.
Yes, 1 over C out. And oh yeah, this one has a denominator 1 over C, so they cancel out. Yeah, good. Yeah, so I was putting it together. Okay. So this is x squared plus y squared times 1 minus v squared over c squared. And this is much neater. T squared. So it's, if velocity was equal to 0, you get back your point potential, right? Then it is r, because this is gone, x squared plus y squared plus z squared, that's r. Right? But now notice z and x and y are treated differently. A positive charge is moving in this direction. That's your z hat, z, and that's your velocity v. And the z direction stays intact, but x and y gets contracted. Right? Everything in the x and y is getting contracted. And what we'll show is that the electric field is what is important here, right? We work with electric and magnetic field. We should see how this contribution goes into the electric and magnetic field. At this point, it just seems that x and y is contracted. This is 1 over gamma, right? And this is z minus vt. But this is only electric potential. We have to now come out and take the derivative and calculate.
So is it always contracted in the perpendicular direction?
No. This is, see, well, the way we should see is that, remember, phi over c and a, right? This acts like a 4 vector. Right? And if I'm moving in the z direction, my gamma will multiply this. I think of your phi times a and your gamma minus beta gamma, or beta gamma and gamma beta gamma. In a moving frame, gamma multiplies this phi and beta gamma multiplies this a. So that gamma is what, so the best way to write this is to pull this out. Right? So the phi is getting contracted and z is also getting contracted. Z is an independent variable. Right? Z gets contracted, phi gets contracted. Phi is also a 4 vector, z is also a 4 vector. So both of them are behaving in a combined manner. We'll come back and talk about this. It's best to see this in the electric field scenario that comes out. So let's stop here and come back next time. Questions? Mostly algebra, but we were trying to put this in the right manner. This one has a reasonably decent expression. That
Can we solve the integral computation like this?
But we did do it, right? Integral? You mean?
Yeah, I mean for a more complicated problem.
Oh, yeah. So this is the challenge. So now answer is no, because this gets in a loop, like to solve for this. See, I mean, if you think about it, a charge is going, if you know its trajectory, then you can solve for its roots. But that's what we're solving for, right? We would like to know its trajectory, or how to say this. Not the dynamics, but in principle, yes. What you're saying is correct. In principle, yes, but I think the point is that the roots are not easily doable beyond a certain equation. Like for a uniform motion, we are getting a quadratic equation. Very quickly, if it is an arbitrary motion, we will get a what do you call a polynomial whose solution will not be easy to do even at a numerical level. I don't want to say that. Yeah, you're saying using numerics, can you do this? I'm just worried about this retardation. Can you capture it correctly? Right. I used to think that it is not easy to capture even using numerics, but now when I'm talking, I'm arguing with myself that no, possibly it is doable. Like I've made the statement earlier that you cannot do that. It is harder to do that. So let me see. So for example, if you have a particle going this way in an arbitrary path, that's your observation point. We know this trajectory, the electric field. So this is your, at time t, this particle is here. But if you want to observe this, it is not this one that will contribute, it is somewhere in the retarded region, right? That's what will contribute. And to get that, get this piece behind. Yeah, I think it is doable.
Yeah, but the question will be if the computer can backtrack actually. I mean, the algorithm can backtrack.
Correct, yeah. And of course, numerical also has its own challenges that roots when it comes, it's not easy, but in principle, it can do it. I think it can do it, yeah. Yeah, I have said this before that I not remember, but maybe I was over, or maybe now I'm missing. Yeah.
So if it is so, I mean, complicated even computationally. So if it is hard computationally, if the problem gets complicated, analytically it will be hard too.
Correct, exactly. This is a uniform charge, right? And now we will see that what we will notice is that most of the time we are not interested in everywhere. We are interested in a region far. For example, an antenna is a very big application here. So there is some charge here which is there. And even if you go a little farther, then you can make this approximation that you're in the far field region. And that's what we will do. And that will be a radiation problem. And it will be significantly easier.
So basically, this is for the base of those kind of problems.
This is for the?
This is the base. I mean,
this is the base. This is the only problem which you can do exactly.
Yes,
right? Uniform motor. Yes, but very quickly we will say that, oh, we cannot do this exactly for other problems. So we will do a radiation problem where we will work in large. And there it will again be solved.
Yeah, that's what going on my mind. I mean, if it is so complicated, why?
Correct, exactly. But sometimes you do need, I mean, if you're interested, for example, in a detector, you really go very close and measure. In principle, it can be done. That's fine. It's just that it might be too tedious. It might take a year for even a normal person to carefully do it. Yeah, so it could be very tedious. Yes. But if it's important, they do it.
But the radiation problems.
That is far region and that is solvable. Right? We will see that there will be a lot of simplicity. Simplicity in our scale, right? Not that it will become like trivial, but it is tractable. Maybe that's the way. Good. Yes.
So as like the velocity, like if it was really, really fast, like proportional to c, then you would have zero potential. Is that the?
Oh, good. No. If velocity, yeah, good point. Okay. More than the potential, we are interested in the electric field. Okay. Let me answer this. Okay. So it's probably a homework problem you will do. So what will happen is that if a positive charge is moving here with a velocity v, in general, the electric field is radially outward symmetric, right? All the field lines will start going this way. As you go faster and faster, these field lines will fold itself. That means it's less dense in this direction, right? They will all focus in the direction perpendicular to it. You go in the extreme limit where V over C is really V equal to C, this will become a line. So it's on a plane. The whole electric field lines will be on a plane. So you're moving, so that I'm moving with all these field lines in a plane. Very dramatic, right? I mean, you don't expect that, but that's exactly if you go very fast. Like if you're very close to this electron when it is moving extremely fast, it may not exert much force because the electric field is very tiny.
So do you get like a Doppler effect for the electric field?
That's correct. All those things will work. Yeah. And we did, we should have, like we did this special relativity that Doppler effect comes in there. It is a relativistic Doppler effect. So yeah, neat things actually. Yeah. Yeah, I should have, I mean, in a normal